Hi, everybody. So let's take a look at the worksheet from chapter 4 that we started working on. We actually did the first question in class last time, but let's just kind of backtrack. So here what we're going to do is we're going to take a look at sampling distributions. And so just recall what a sampling distribution is. We have some population X, and what we're going to consider is when I take a random sample from that population of size N and look at some statistic like a mean or a proportion of that sample. Then we can pick another random sample, and we repeatedly pick random samples over and over again, each of them the same size N, and then we can look at the distribution of the sample statistics that we get. So the example we looked at in class last time was the population where we have all CU Denver students. And we know from population data that 60% of students are undergrad, 40% are graduate. And so what we want to describe here is what would the sampling distribution for the proportion of students in a random sample, in this case of 100 students at CU Denver, what would the distribution of sample proportions look like? So first we can take a look at, well, what would the mean of this sample distribution be? So I'm going to let that be denoted with a mu with a subscript of p hat. And this is going to equal the expected value of the sample proportion. That sample proportion we can think of as x, which were what were the number of students out of 100 that were undergrad. And so that's going to be determined by a binomial distribution where we have 100 students, and the probability of a success of picking an undergraduate is 60%. So that expected value would be how many students were undergrad out of the 100 divided by the size of our sample, which is 100. And so with this expected value, recall we can pull out a constant, and then what we would get is 100 times the expected value of x. And when we have a binomial distribution, the expected value is equal to the value of n, which is 100, times the value of p, which in this case is 0.6. So our expected value is equal to 0.6. So mathematically, we see that we should get a sample that has approximately 60% undergraduates. Conceptually, intuitively, this should make sense. If our population has 60% undergrads, I pick a random sample of 100 students, I would expect about 60% of them would be undergrads. For the variance, say we want to calculate the standard error, I'll just say the variance of p hat. Well, this would be the variance of p hat is just x over 100. And when we're dealing with variances, remember it's the expected value of x squared. So when we pull out constants, we actually pull out 1 over 100 squared times the variance of x. And when we have a binomial distribution, as in this case, our variance, we have the 100 squared, is going to be n times p times 1 minus p. So we've got 1 over 100 squared times 100 times 0.6 times 0.4. And so the 100s, at least partially, cancel out. And what's left is 0.6 times 0.4 all over 100, which works out to be 0.0024. So there's our variance, and therefore the standard error would be the square root of 0.0024. 0.24. We'll just think about the variance instead of the standard error. So for this case, for this example, we found, let's say, the variance to be 0.024. We found the expected value to be 0.6. So question 2 is now asking, well, what happens if we increase our sample size from 100 to say 200 students or 500 students? And so if we increase the sample size, one important thing to note here is the expected value of the sample proportion is still going to be 0.6. If you think about it, if we pick larger and larger samples, we calculate the mean, what proportion of students in that sample were undergrads. Even if we increase the sample size, we would still expect to get the proportion of 0.6 because that was the proportion from the population we are picking from. So that doesn't change. When we increase the sample size, the variance, however, is telling us, well, how much variation in the sample proportions do we get? When I pick a different sample, how much are these sample proportions varying? And so when I pick larger and larger samples, we would expect less variation. Since the larger our samples are, the less error we're going to have due to the sampling process. So we would expect this variance to get smaller as n gets large. Okay, so now we've looked at this kind of thinking mathematically using properties of expected value and variance that we know from binomial distributions. We thought about why it makes sense intuitively that we would get a sample proportion which is close to the population proportion each time. And intuitively, hopefully, it makes sense that the larger we make this, the less variability we have in sampling, the smaller the variation becomes. And so let's kind of run some simulations to check and make sure that our intuition seems in line with what simulations are telling us. So here, some R code down here. And so what I'm doing here is saying, let's say we have samples of size 100, and we have a probability of success of 0.6. So anytime I pick one person out of the 100, the odds that they're an undergrad is 0.6. And I'm going to pick this, I'm going to repeat by picking 10,000 random samples, each of size 100. So this is going to simulate picking random samples of size 100 over and over and over again. And I'm checking out the code down here. We have a loop, so as I goes from 1 up to 10,000, what we're going to do, this is a command which is saying randomly pick one number out of a binomial distribution from n trials with a success of p in each trial, and then divide that by n. So really what we're doing is, this is calculating a sample proportion. So this is saying randomly pick a number of successes that you pick from a binomial distribution and then divide that by the sample size. So results is showing all of the sample proportions, and then we can make a histogram displaying that sample proportion. So this code is posted up in Canvas so you can play around with it. And then what we can do is just change our sample size from 100 to 200 to 5,000, 1,000, etc. So let's see what that looks like. So here we've got 4 different plots. So this is the sampling distribution for the proportion when n is 100, 200, 500, and 1,000. And so what we can see is that, yeah, all of these distributions, they're all centered at 0.6. So the red line in the middle is all at 0.6. But as n is becoming larger, what's happening is the variance or the standard error of these distributions is getting smaller. The distributions are getting less and less wide. They're getting narrower because we have less variability in the sample statistics. And so this table is comparing kind of the exact values that we would get if we did the math to calculate the expected value and the variance. And over here are the values that we get if we, instead of doing this exactly, we just ran a bunch of simulations and then calculated the center and the spread of those simulations. And what you can see is pretty much everything, the exact value in the simulations are almost exactly the same in all of these cases. So we do observe that even as we increase the sample size, the center of the sampling distribution doesn't move, but as we increase the sample size, the sampling distribution is getting more and more narrow. Okay, so we're going to take a look at some other examples in a second, but just to back up, when we're working with sampling distributions, we'll see we've already thought about different ways that we can calculate probabilities with sampling distributions. So one is using the simulations that we just did over here. So rather than calculate these exact values, I can just have our randomly generate tons and tons of samples and then create a sampling distribution. And this is what we've done with permutation tests as well. We can run approximations using the central limit theorem. We've seen this a little bit, and we'll see some examples in this packet using the central limit theorem. And we can also do some exact calculations. So that's what we did in the previous example with p hat before we then ran the simulation. So I want to illustrate, we've already illustrated the simulation method up here, but I want to work on how we can do exact calculations and how we can use the central limit theorem to do some approximations for us. So I'll post some separate videos with some of those examples.